All right, so in the previous recording, we talked about the small signal model for a BJT. We saw that we can make an amplifier, introduced a small signal model. Very quickly, I'm going to go through how we can make a small signal model for a MOSFET and then analyze a MOSFET circuit and see how it behaves as an amplifier. So here's the circuit, and again, because this is very similar to what we did with BJT, I'm going to skip all the detailed explanations. You can refer to the textbook, and if you followed the discussion on BJT, this should be fairly similar, and really doesn't need to have as much time spent on it. If you have questions, we can always discuss them during the live sessions as well. So if you go and draw the V out, V in relationship for this circuit, similar to what we had for a BJT, we have a behavior like this. Difference is that with a BJT you hit almost a hard limit at the saturation, and VC sat will not change. With a MOSFET, you don't hit that. It's a softer landing. You go into triode region, you lose the current source that you had, but now you have a nonlinear variable resistor. It's a little bit of a softer curve, but again, like a BJT, we go and bias this device at the desired VGS, let's say, and you get the desired V out at DC here. Now, if VGS goes up a little bit, so it's changing by, let's say, VGS plus, changes to VGS plus, small VGS, which represents the changes, your V out, in this case, you can see is going to go down to V out plus V out, but you can see right away from this diagram that V out will have a negative value. And you go and do the math, and we're supposed to solve this circuit with a large signal approximation, a large signal assumption here. Right? So go and see what an increase in VGS does to I out and try to estimate the gain from there. I'm going to move past that, so I'm assuming that you will do this on your own. What I'm going to do is that I'm going to go and build a small signal model for a MOSFET. In this case, an NFET, let me draw an NFET here. What I want to do is similar to what I did for BJT. So I want to go and say, if this little ID here is in response to a small signal applied to the gate of this device, how can I come up with a small signal equivalent circuit for this transistor to just do the DC analysis first, but then after that only focus on the changes. So I want to see what relates this little ID here to this little VGS here. So I will come up with that model. The large signal model that we had for a MOSFET was this. It was simpler than what we had for a BJT because at the input you have an open circuit, right? It was the gate of the device that we always said has zero current. At the drain end you had a current source if the device is in active region whose value was 1/2 mu n C oxide W over L times VGS minus VTH squared. Okay? So this was the large signal model that we used to solve MOSFET circuits. And the question is that once you do that, how do you account for small variations? So if this VGS at the gate for this device changes by a small amount, how will you take into account the changes at the drain terminal? And then the answer is that you go through the same thing that we did for a BJT, and in this case you actually come up with a simpler model. At the input, for a BJT you had that diode that appeared as a resistor R pi in your small signal model. For a MOSFET, an open circuit shows up as an open circuit. And you will still get a GM VGS here for the current source, but the GM is, well, not what you calculated for a BJT. So remember what we had for GM for BJT was the changes of IC due to the changes of VBE, right? The slope of that curve for a BJT, right? MOSFET is the same. So if you go and calculate delta ID in response to VGS, you can estimate that GM for a MOSFET, right? The transconductance for a MOSFET, therefore, is going to be, well, you know, I'm going to take the derivative of this expression, so 1/2 mu n C oxide W over L VGS minus VTH squared with respect to VGS, and see what happens. So if you take the derivative of this term, well, all of this part is constant. The two that you have in power will come in front of this, and then the derivative of VGS minus VTH is just 1. So if you do the calculations, it's going to be mu n C oxide W over L times VGS minus VTH. So while in BJTs it was the DC current IC that set the value of VGS, GM, in here GM is set by VGS minus VTH. That's the DC parameter that comes into play to set your transconductance. If you want, you can just go and expand it. You know, you already know this expression for ID and VGS. You can play with it and then come up with alternative expressions for GM. So for example, you can say that GM is 2ID over VGS right? So if you don't want to use the small signal, the transistor parameters, the technology parameters here, if you know ID and VGS minus VTH, you can directly calculate that ratio to give you GM. You can show that it is the same thing. Or you can say it's the, let me just, you can just multiply this by mu n C oxide, and you can see that this is 2 mu n C oxide W over L times ID. Take the square root of that, and this also gives you this expression here, right? So I basically multiplied the expression that you see over here with 2 mu n C oxide W over L. Take the square root of that, you get the equation at that end. These are alternative ways of calculating GM. So if you have VGS minus VTH and then the transistor parameters, use this equation. If you have ID and transistor parameters, use this equation. If you have ID and VGS but not the transistor parameters, use this equation. All of them give you the same thing. The goal or the end point is that it will be the slope of ID VGS curve, right? So we have the quadratic curve between ID and VGS. Well, this is more like an exponential now, right? So this is VTH. Before that, you don't get anything. And this is your bias point, assumingly. So this is the slope here. And that's the value of GM. Calculate GM from your DC analysis, put it in that model, and then there, bingo, you have your small signal model for your N MOSFET. And good news here is that for P MOSFET, similar to what we discussed for PNP and NPN situation, the small signal model for a PNP transistor is also exactly the same as what you have for, for an P MOSFET is exactly the same as what you have for a P MOSFET. So that's good. A P MOSFET and N MOSFET, you do a DC analysis, separate DC analysis, but once you get to the AC stage, basically the two are the same. So what I'm going to do now is solve an AC problem. So here is an example.
I didn't get that. Could you try again?
Okay. Here is an example. I have a, let me see if I have a PMOS example. I have a PMOS example. I'd like you guys to try it and come and ask me questions during the live session. If you cannot, if you need help with it. I'm going to solve the NMOS problem that I have here because it looks a little bit more interesting. So here's the circuit. Okay, so I have a circuit like this, right? So a resistor is connected between drain and gate of this transistor. I have an RD of 10 kilo ohm and RG of 10 mega ohm. You see two coupling capacitors here. We discussed the role of these coupling capacitors before. What they do for me in these kinds of applications is that they separate the DC operating points of different parts of the circuit from each other. So what you have in here for the transistor has some DC values for those nodes, and then let's say V in has 0 DC. So if you connect V in directly to the gate of this transistor, you put a 0 volt DC voltage at the gate of that transistor and turn it off, which is not the case. You want, or which is not what you like. You want to have a transistor in active region. And therefore, by putting a capacitor there, the gate voltage can be DC, some DC other than 0, depending on how you bias it. And V in can be happily behind the capacitor. For RL, the same thing. By putting a capacitor between RL and the transistor, the drain of the transistor, I make the drain voltage independent of the DC voltage that I have at the RL end. And again, I have 0 volt DC over there. If I connect it directly to the drain, I'm going to mess with the DC voltage or DC bias point of the circuit. So I put a capacitor there, make my life easy, and separate the DC operating points of the left and right of that capacitor from each other. There is a price to pay. Obviously, you know, if your signal is very low frequency, you have problems here. You do not, you cannot pass a low frequency signal through this system. But the idea here is that you assume the capacitors are so large that their impedances at the operating frequency of the circuit is negligible, and therefore at kilohertz frequencies or gigahertz frequencies, whatever it might be, they're appearing as a short circuit for your signal, but at DC a capacitor is an open circuit. So what I want to know is find out AV, R in, and R out, right? All small signal parameters. I need to solve the DC circuit first, even if I'm not explicitly told to. So the device parameters are a threshold voltage of 1.5 volts and mu n C oxide W over L of 0.25 milliamps per volt squared. Okay, I go and solve the DC circuit first. Solve DC. I need to assume an operating region. Fairly easy here. I can see that the drain and source, the drain and gate are connected, so VGD is 0. How do I know that? Well, convince yourself that VGD, the voltage drop from here to here, is 0. Hint, the gate current is 0. So VGD is 0, and this is already less than VTH, what I need to create a channel at the drain end. VGS, if VGD is 0, VGS, it looks like it can be larger than the threshold voltage that I have. So it looks like active region of operation is a possibility. Definitely not in cutoff, not in triode, because my drain gate voltage is 0, it must be larger than V threshold if it is in triode. Definitely not triode, could be cutoff or active. I'm going to assume active and solve the circuit. Write a KVL in this loop. So I go around this device and go to ground. Note that I do not take this path. This is another path. I can go from here to ground. So in that case, I go and say VDD is equal to the voltage drop across RD plus VDS, but VDS is an unknown. It's a voltage drop across a current source if the device is in active region. I don't have anything that tells me VDS for a current source. So I take the alternative route. I don't go there. I take the alternative route and go through VGS. If I write my KVL, VDD is equal to IDRD. So this voltage plus the voltage drop across RG plus IGRG plus the voltage drop here, VGS. And knowing that IG is 0, so this is already 0, I know that. Assuming active means that the voltage current relationship is given by this expression. Plug this value in there and you can, well, the solution is similar to what we did before. To save time, I'm just going to write the final answer. ID is 1.06 milliamps. Now I'm going to skip 2 steps. The first step is that, you remember when I solved the quadratic equation, I get 2 answers. So go and see what the other answer was and why did I pick this answer instead of that? How did I reject that? And the second question is that, okay, so once I have this and I assumed active, I need to verify my assumption. So after this, I need to verify the assumption. You do that as well. Show me that VGS is larger than VTH because the other one we already checked. Okay? So I'm going to leave those 2 steps to you. I'm going to jump to the small signal part that is a bit more exciting. Now, with the DC analysis away, I have to create my small signal equivalent model for the circuit. I put my transistor first. Usually you have very few transistors in your circuit, 1 or 2, and I attach everything else to them. So start with them at the center. The source of this transistor is grounded, so that's that. What I have in the drain is RD that goes up to ground, right? Again, the DC source at the top, VDD over here, will be ground for AC analysis. I don't like the way it looks like, so I'm going to just draw it down here. Okay? And then I have the coupling capacitor and RL. So what happens is that the coupling capacitor is assumed to be short and RL here. And this is V out. At the input, again, I have a coupling capacitor which is assumed to be shorted. And the input source. And between the drain and gate, I have RG. So this is the circuit that I want to solve. And if you wanted to solve this using the large signal model, it can take a while. So first thing that I want to find out is the voltage gain, so V out to V in ratio, then the input resistance and output resistance. The input resistance is what I see when I look into the amplifier. Output resistance is when I look back. So output resistance is taken before the load resistance. Input resistance is taken after the source. And your source may have a source resistance. So all of those are going to be behind the node where I look for my input resistance. So if I go and take that, R in and R out are measured from here. So I need to do that separately, right? The first step is to figure out what is gain, what is the voltage gain that I have here. Okay, so I go and try to figure out a relationship between V out and V in by solving this circuit. Write a KCL at this node. If I write a KCL and node V out, I can say this current plus this current plus this current plus this current should add up to 0, right? So V out over RL plus V out over RD plus GM VGS plus this current is going to be V out minus V in divided by RG, this current, right? Plus V out minus V in divided by RG is 0. And I noticed right away that, I want to make my life easier. So I noticed that VGS, the voltage here, is the same as V in, right? I'm applying the source end is ground, and I'm applying that voltage directly to here. So this is V in. I already have a relationship between V out and V in. And so I'm going to make it explicit here. Since VGS is equal to V in, I can see that V out times 1 over RL plus 1 over RD plus 1 over RG. So this is V out on one side of the equation is equal to V in, and then I put everything that has V in it in the second side. It's 1 over RG minus GM. Okay? And you have ID value. You can calculate GM here from ID. It turns out to be 0.73 millisiemens, right? And if you plug that into here, you can show that AV, that is the ratio of the output signal amplitude to the input signal amplitude, is going to be minus 3.6 volts per volt. Right? So I put volts per volt so that we know it's a voltage amplifier. Voltage at the input, voltage at the output. I'm explicit about it, right? Okay, so that's that. This circuit gives me a gain of almost 3.6. What about the input resistance? Okay, I take the small signal circuit that I have here, detach all the independent sources from it, attach my test source to the input, and do my measurement of the current from that source. Well, okay, so I detach the independent sources and attach my test source to the input. And then I measure the current that comes from the test source. Now, good news here is that my circuit didn't change, right? The circuit that I had with V in is the same as the circuit that I have with V test. So I can actually save some time here and use the calculations that I had before. I can see that I test is VGS minus V out divided by RG, right? The voltage here minus the voltage here divided by RG, because all of the current from the source goes through RG. And because I already know V out is AV times VGS, and VGS is, this is VT, and this is AV VT, I can quickly solve that. And after you do the math, you have a value for IT. R in is going to be VT over IT, or let me just call it X, because I don't want to bring another thing that has T in it so it doesn't get mixed up with thermal voltage or threshold voltage. So IX is Vx over Ix. And if you do the calculations, it's going to be 2.33 megohms. Okay, so this was lucky, right? We just removed the source and then attached our test source here, but we ended up with the same circuit. If you're careful, in most cases, you can actually do this and reuse the circuit that you have for gain calculations to calculate the input resistance as well. The output resistance is a different story. If I want to attach my test source to this circuit, I'm going to deal with a new circuit. So it's a different story. I'm going to redraw that circuit for output resistance. So I remove RL. I'm looking from before RL. I remove my independent source at the input. This is what I'm going to have. So this is the gate source terminal, the GM-VGS thing. source is grounded. Now, remember here I had a gate that was connected to a voltage source. If I remove that independent voltage source, if I zero it, this is what I get. RG here, this is VGS. So that's the transistor and RG. Then at the output I had RD. And now this is where I attach my test source. So let's just call this, I don't know, VY. And I want to measure IY to estimate the output, to calculate the output resistance. Now, first thing I noticed here is that VGS is 0. The gate is connected to ground, the source is connected to ground, so VGS is 0, and therefore VGS is 0. Okay, so the current source is out, so if I look at IY that goes into this node is going to be the voltage at that node divided by RD plus, RG, so there's a component of current going here, component of current going here, right? And this current we just calculated to be 0, plus VY over RG, okay? Or it's VY times 1 over RD plus 1 over RG. All right? So therefore, R out, which is the ratio of VY over IY, is going to be 1 over RD plus 1 over RG, the entire thing in a denominator of a fraction, or we know how to write this. It's RD in parallel with RG. And that will be the small signal output resistance. So there is a PMP example, P MOSFET example for an amplifier. There are examples for PMP, BJTs in amplifiers. I encourage you to solve a few of N-type and a few of P-type devices, NPN, PMP, NMOS, PMOS, using the small signal model. Convince yourself about, the behavior of the circuit. Try to get a feeling about how it works. Do the calculations using the small signal model. Make sure that you draw a lot of small signal equivalent circuits. We're going to deal with these for the rest of this semester. So they're very, very important. So make sure how you go from a circuit that has DC and AC components into it, and do the DC analysis first, then draw the small signal parameters, draw the small signal circuit, build that, get rid of the coupling capacitors and DC sources and all that, and then use that circuit to estimate small signal quantities. So that will be it, and then for the next lecture we'll talk about a couple of, 3 actually, standard configurations for single transistor amplifier stages. These are simple stages that we will analyze using the small signal analysis that we learned here. And if you know those 3 stages well, you basically can, I think in most cases, 90% of cases, satisfy the needs for transistor amplifiers in your future roles. So that's it for today, and thank you.